please do. I'll start at the front here on this side, and whoever gets it back at the back, you could send it along the back and have them send it all the way around, so that the goal is to have everybody sign in, please. That'd be great. Secondly, I would like to know your opinion of the pace of the course. Am I going about right, or too fast, or too slow? So I'm going to send this around the room in the same way, and just put an X or a check mark next to the pace that is your opinion of how the pace is going as well. And whenever that's finished, if somebody could bring it up to the front, that would be great. Thanks. All right. So let's get back to where we were. So that's the classical approach. Then, much later, these are actually out of historical order. The classical story was 1650. The Bayesian story was about 1750. And then in around the year 1880 or so came the frequentist story, which is due principally to the guy John Venn, who's famous for Venn diagrams, and also it was made more rigorous by Richard von Mises and also by Kolmogorov. And the idea in the frequency story is completely different from the classical story. In the frequency story, you have to restrict attention to attributes, capital A, of things called events, namely phenomena that are inherently repeatable under conditions that are as close to identical as possible. So now you want to think about, for example, a roulette wheel. The American roulette wheels have 38 slots in them, the numbers 1 through 36, alternately colored red and white, red and black, and the numbers 0 and 00 colored green. And you want to imagine spinning the roulette wheel once and having the ball come to rest. And an idealized roulette wheel would have the property that all 38 of those elemental outcomes are equipossible. Now in the frequency story, you have to imagine spinning it again, and spinning it again and again and again and again, and keep track of the relative frequency with which something interesting to you happens in those repetitions. And hope that in the limit, as the number of repetitions goes to infinity, you get a stable answer. And if you do, that's the frequentist definition of the probability of interest. So the frequentist probability of getting the number 6 on an idealized roulette table is the limiting value of the relative frequency with which you get a 6 in the repetitions, the hypothetical repetitions, as the number little n of repetitions goes to infinity. Completely different way to think about probability. Then the third approach is sometimes called the personal approach, sometimes called the subjective approach, sometimes called the Bayesian approach. And there have been two quite different ways to define the Bayesian story. One is due to Mr. Bayes himself. He was a minister in England for his day job, a kind of minister called a nonconformist minister, meaning that he was not Church of England. Even today, England still has an official state religion, the Anglican Church. But he was, I think he was Episcopal minister or priest, and that made him a nonconformist. That was his day job, but he was an amateur mathematician at night, and he worked out the basic story behind conditional probability and used it to develop what we now call Bayes' theorem. That was his big contribution. In fact, he used Bayes' theorem to solve an inferential problem, and he regarded his work as sufficiently controversial that he was not quite ready to publish it yet when he died. And so the world might never have known about his story, except that a friend of his called Richard Price, both of them were fellows of the Royal Society. Richard Price went through all of Bayes' papers after Bayes died and found this wonderful material. And because Richard Price was a good guy and not a bad guy, he collected Bayes' work together and touched it up a little bit and then polished it, rather than published it under Bayes' name posthumously. A not-so-good guy would have published it under his own name, Richard Price, and we might be talking about Pricean way of looking at probability. But Price was a good guy, and he actually said to the world, this is what my friend Mr. Bayes figured out, and you should think about it too. And the person who came along after Bayes, who is most in the spirit of Bayes, is a great Italian statistician and actuary named Bruno De Finetti, who did much of his greatest work in the 1920s and 30s. And so this definition of probability is, again, completely different from the other two. You have to think about betting and think about betting odds. So imagine betting with someone about the truth of the true-false proposition A, for instance, in our case study, that this person is HIV positive. So imagine betting with someone about the truth of that proposition, and you ask yourself what odds, I'm going to call it capital O for odds, subscript U, what your odds are in favor of that proposition. So what odds you would need to give or receive in order that you judge the bet to be fair. In other words, you would be prepared to take either side of such a bet. That odds can then be converted into probabilities in the usual way for odds. You may recall that odds work like this. If you've got the odds of something, the probability is odds over 1 plus odds, as long as the odds are expressed in favor of the proposition. So P equals O over 1 plus O. And then if you solve backwards, you get odds equals P over 1 minus P. So it represents the chance of the thing being true divided by the chance of it being false. That's the odds in favor of it being false. These things are used a lot in things like betting at the horse racing and other sports issues. And so once you've worked out those odds, then you just go odds over 1 plus odds, and that's your personal. So P subscript B for Bayes, colon U, those are your personal odds, which lead to your personal probability that A is true. And the U in there explicitly acknowledges the fact that this way of looking at the world is personal to you and is, quote, subjective, by which we mean it's based upon your assumptions and your judgments and, most importantly, your information. Two Bayesians can have quite different probabilities for the same event if they have different information bases. And that's as it should be. This is something that Mr. Venn didn't understand. We're going to talk more about his idea of so-called objectivity a bit later. But essentially, if probability, I said at the beginning, statistics is the study of uncertainty, and I should have defined what uncertainty is. Uncertainty is a state of incomplete information about something of interest to you. In other words, statistics is about information. And so if probability is trying to quantify uncertainty, and uncertainty is about information, then naturally two people with different information bases will have different probabilities. And that was something that Mr. Venn didn't want to happen. He wanted science to be such that everybody always got the same answer in every problem that came along. In the same way that when you're doing math in elementary school or junior high school or high school, there was always a right answer to every problem. Well, in fact, that's not true in statistics and probability. Different reasonable people with different information bases can end up with different probability assessments. And actually, even different reasonable people with the same information bases and different assumptions and judgments about how to bring that information to bear will come up with different probabilities as well. And we have to be prepared to account for that in our theory of probability. And again, Mr. Venn's approach to things doesn't have any room for that. So that's one way to think about the Bayesian story. And it is explicitly personal and subjective, so it has B colon U. Someone else's U sub 1, B U sub 2 would have potentially a different number. And there's a wholly different way, which I like better, which started out with Laplace and then was continued by an American physicist named Richard Cox, who is not as well known as he should be, and then continued more directly by a wonderful mathematician and electrical engineer and physicist named Ed Janes, and he's the person who wrote the third book that I actually should have brought with me today as well. I'll bring it next time. For these people, and for me, this is my favorite definition of probability, the Bayesian probability for you of the truth of proposition A is a numerical measure of the weight of evidence in favor of proposition A based on your current information, and we require that the nature of these probabilities to satisfy a set of reasonable axioms that forces them to achieve internal logical consistency. And Mr. De Finetti had the same thought about logical internal consistency, and he expressed it in terms of betting with a concept that's called Dutch book. Suppose I quote the probability of rain. Let's say there were a rain gauge on the roof of this building, and we would agree that we're going to call rain occurring if in the 24-hour period starting at midnight tonight to the midnight the next night, the accumulation of the rain gauge was at least 1 millimeter. So that's a pretty hard and fast way to think about rain or not. If you quoted a probability of 0.7 of rain and of 0.4 of not rain, Mr. De Finetti can show you that your probability, your joint probability assessment of rain and not rain is logically internally inconsistent. He called that incoherent. And the way he showed it to you was he showed you that because each of those numbers was supposed to be based on betting, he could offer you a set of bets which would have the property that no matter whether it rained or not, you would lose money. And that would be a direct way to show you that there was a logical contradiction in your announcing 0.7 for rain and 0.4 for not rain at the same time. Same idea, except nothing about betting odds. Basic, simple principles and axioms that leads to the same kind of internal logical consistency in the system based on Laplace and Richard Cox and Ed Jaynes. Now, each of these, there are other approaches. Fisher tried to create one called fiducial probability that turned out just to be Bayes under wraps, so to speak. And several people tried to create something called logical probability that also, it's like one of those old pictures of people trying to invent a flying machine. It gets off the ground a little bit and then crashes. And so their approach actually does get off the ground, but then it crashes in problems of serious complexity. So I'm just going to talk in this course about the classical story and the frequentist story and the Bayesian story. And pretty soon I'm going to stop talking about the classical story because it turns out it doesn't work very well in problems of realistic complexity. So each of these probability definitions, it turns out, has pros and cons, has pluses and minuses. None of them uniformly dominates the other. The classical approach has the great plus that it's really simple when it's applicable, when you can actually enumerate the elemental outcomes in a way that makes them equipossible. So all the stuff you heard about in elementary school about idealized coin tossing and idealized dice rolling and stuff like that, that all can be covered perfectly well with the classical approach. But there are a number of difficulties with the classical approach. As soon as the number of elemental outcomes is infinite, you're in real trouble. What's the classical probability that you'll get an odd integer if you choose an integer at random from all integers, from minus infinity to plus infinity? The classical approach has no narrative for that because the numerator and the denominator have to be finite in the classical approach. There's no limiting concept in the classical approach. You just count things. And if you've got infinity over infinity, you can't do anything with it. Also, there's a problem in trying to define equipossible without a circular appeal to probability. And the only way to do that is through something that Mr. Laplace called the principle of insufficient reason. In effect, you judge elemental outcomes equipossible if you have no grounds for favoring one of those outcomes over another, and those grounds might be empirical or logical or based upon symmetry. This turns out to lead to paradoxes when you're working with infinite sets. The assertion of equal uncertainty on an infinite set is not, as it turns out, invariant to the choice of scale, and nor should it be. And I'll show you what I mean by that. Suppose you were uncertain about a quantity theta that lived from 0 to 1, and you tried to use the equipossibility argument. Then we're going to get in the habit in this class of expressing uncertainty about numerical quantities by writing down probability distributions for them. That turns out to be the best way to quantify uncertainty for something uncertain that's a number. You build a probability distribution that expresses your uncertainty. And so if really all the outcomes between 0 and 1 were equipossible, then that would give rise to a completely flat distribution, which, as you know, people call the uniform distribution on the unit interval 0 to 1. And this is something that bothered Fisher also. Fisher said, well, if I don't know anything about theta, then okay, you say I should put a uniform distribution on that to describe my uncertainty. But shouldn't that mean that I also should put a uniform distribution on theta squared, or the logarithm of theta over 1 minus theta? There's all these other different scales you could imagine being equally uncertain on. And Fisher thought that if you were going to put a uniform distribution on theta, you had to, at the same time, be prepared to put a uniform distribution on all those other transformations of it. Actually, that's kind of a silly thing to say because, in fact, if you really don't know anything about theta except that it lives between 0 and 1, you actually know quite a lot about something like theta raised to the power 1,000, don't you? Because if you take a number less than 1 and bigger than 0 and raise it to the 1,000th power, what's it going to be? Take a number like 0.9 or anything you want and raise it to the 1,000th power, it's going to get smaller, right, every time. And so no wonder. This obviously can't be a uniform distribution over here for theta to the 1,000th, and it was Dennis Lindley who pointed that out and showed Fisher that his position was silly. But anyway, there are potential problems with the classical approach, and I'll mention the third one is essentially that in problems of realistic complexity, Suppose you're working with a big data set in a Google application or an eBay application or anything else anybody in the room is working on. It is extraordinarily difficult to invent a concept of elemental outcomes that are equipossible. And that reduces everything to counting. None of the problems I've ever worked on with people at eBay or Yahoo or any of the tech companies I've ever worked with have had the ability to break the problem down into elemental outcomes that are equipossible. It's just not possible in problems of realistic complexity. So that was a great thing to get money, for Pascal and Fermat to get paid money by that guy, Chevalier de Marais. And it's also a great thing for teaching simple probability concepts to people in elementary school. But that's as far as the classical story goes. It just can't cut the mustard for hard problems. And so I'm not going to talk about it anymore. The frequency story has the great plus that the mathematics of it are relatively tractable. And indeed, people in the 20th century have proved many useful theorems about that, because it turns out the math is not that bad. But it has the minus, among various others, that it only applies to inherently repeatable events. So for example, roll the clock back to November 2011 and ask yourself, what's the frequentist probability that Barack Obama would be reelected in 2012? What is the repeatable collective into which we can embed Mr. Obama's either being reelected or not? That's actually a hard question, a kind of embarrassing question for frequentists. So you could say, well, let's see. He's a Democrat. Let's have the repeatable collective be all the presidential elections in which a Democrat was elected president and then ran for office again to be reelected. You could create a frequentist probability that way, maybe, and think of Mr. Obama's reelection as like a random sample of size 1 from that little repeatable collective. But that's probably not a very good probability assessment, because there's all sorts of special circumstances connected with Mr. Obama. He isn't just a Democratic president trying to be reelected. He's a Democratic president trying to be reelected on the tail end of the worst recession in American history since the Great Depression. And he's a black man, and he's this and he's that, and you keep going, and pretty soon you find he is a one-off. He's unique. There's no repeatable collective for him. The frequentist probability back in November 2011 that Barack Obama will be reelected in 2012 is undefined. He either is going to be reelected or not. The closest you could come from the frequentist point of view is to say the probability is 1 if it turns out that he is, and it's 0 if it turns out that he's not. And in fact, I have heard frequentists, I've asked them this question, and they've said basically, ask me again after November 2012, and I'll tell you what the probability is. What's the frequentist probability of life on other planets? You can't do it. There's no repeatable collective story that you could tell. What's the frequentist probability that Shakespeare wrote all the stuff we attribute to him? There's very definitely no repeatable collective that you could embed that in. And more to the point with my case study, what's the frequentist probability that this guy is HIV positive? He's just a one-off. He's not part of any repeatable process by design. He wasn't chosen at random from a bunch of people. He's just a guy who walked into your doctor's office. So strictly speaking, the frequentist probability that he's HIV positive is undefined. And I'm about to show you in a minute that there's a kind of a trick, sort of a dodge that people use to create something that's like a probability that frequentists can talk about, that's sort of like what we want. The result of the survey is that almost everybody thought it was about right, a little bit too slow, and one person too fast. And I think I'm just going to keep going at this pace. I hope that's okay for the people who thought it was too slow. It's going to get harder later on. Don't worry. This is the section called background and basics. So there's lots of things you're uncertain about that you can't even talk about with the frequentist approach. Indeed, anything, strictly speaking, anything that involves a purely observational phenomenon, you're gathering data, and instead of the data being the result of a randomized sample survey or the result of a randomized controlled trial, you just see what happens with people with this particular version of the web page at Google, for example. And you don't compare it in a randomized controlled fashion with some other version of the web page in an A/B trial, for example. You just look and see what happened. That's observational data. Strictly speaking, the frequentist story can't tell you anything about what's going on in there, because there is no obvious repeatable collective in which you can embed that story. So, frequentist story, great if you can apply it, because there's all this great math, but you can't apply it to a lot of things that you really are uncertain about. The Bayesian story has the great plus that all forms of uncertainty are in principle quantifiable with this approach, but it has an important minus that I already mentioned in the first session. Namely, you're going to see in the Bayesian calculations that there's no guarantee that the answer you get, either by querying yourself about betting odds or weight of evidence, will retrospectively be seen either by you or others as a good answer. We're about to find out in the Bayesian story that it's possible to get really bad answers from the Bayesian story by putting information into the Bayesian machinery that is seen after the fact to have been badly out of step with reality. The machinery is expecting that you use good information, and it tells you how to combine good information into a good information summary. That's what the Bayesian story does for it. The Bayesian machinery by itself does not check the quality of your information. It just tells you how to combine it if it were good information. The same is true, by the way, for the Frequentis story. There's no guarantee in the Frequentis story that you get a good answer. If you have bad information or you process it badly using Frequentis methods, you'll get a bad answer in the Frequentis story also. But the crucial thing about the Bayesian story, as I mentioned in the first session today, is that there's nothing in the Bayesian story that forces you to be worried about calibration issues. There's nothing in the Bayesian story. There's no part of the Bayesian narrative that forces you to pay attention to how often you get the right answer. And for me, that's the single most important minus of the Bayesian story, and that's why I suggested that fusion that I was talking about in the first session. All right, well, let's try applying this idea to the HIV screening case study. Again, A is the true-false proposition that this patient is HIV positive, and we want to know what P of A is. We actually do have background information. We have data available from medical journals on the prevalence of HIV positivity in various subsets of the population of all humans. For example, it's higher in gay people, it's lower in older people. There's various other relevant factors. As statisticians, we would call those variables covariates or predictor variables. It turns out that all three of the probabilistic approaches require you to use your judgment. And this is the reason that Mr. Venn was wrong in trying to create a notion of objectivity in which everyone always gets the same answer in the realm of probability, because every uncertainty assessment anybody has ever done is inherently judgmental. We have to bring our judgment to bear. Now, there is a Bayesian narrative of objectivity, namely that when we all try to bring our judgment to bear reasonably and we all turn out to get more or less the same answer, then that's a certain sense in which that particular probability assessment is objective, because we all got pretty much the same answer. But the notion of being able to remove judgment entirely from the process of assessing probabilities is crazy. It's like trying to remove judgment entirely from the process of doing science. It cannot be done. And yet we know good science from bad science, and it has to do with whether the judgment that was exercised in the science in question was good or bad. In the same way, we know good probability assessment and bad probability assessment according to the quality of the judgment. So here comes a big judgment. And Fisher actually, interestingly, toward the end of his life, wrote about this. He created the phrase recognizable subpopulation, and it connects with an idea, a Bayesian idea called exchangeability also that I have written on. You have to use your judgment to identify what's called the recognizable subpopulation. Let's call it script P, subscript this patient. It's the largest subset of the set of all humans to which this patient belongs, for which the HIV prevalence differs from that in the rest of the population by an amount that you judge to be large enough to matter in a practical sense. And that's a mouthful, but the basic idea is that once you've identified this recognizable subpopulation, it's a sort of analysis of variance concept for those of you who have seen that before. Within this recognizable subpopulation, each person, it's as though each person has a different prevalence of being HIV positive, but you regard all those prevalences as close enough to constant so as it's too small, the differences are too small to matter, but the differences between HIV prevalence in that subset and everybody else are big enough to matter. That's the idea of a recognizable subpopulation. And so here's a couple examples, if I can get this thing to come up. If the script P is all humans, and we divide people, it turns out that gay people have a higher prevalence of HIV than non-gay people do. And so if we divide the world into gay people and non-gay people, according to along the dimension or predictor or feature sexual orientation, we find out that the prevalence of HIV in the gay subset might be 0.02 and in everybody else might be 0.0005. And you ask yourself the question, is that difference between 0.02 and 0.0005 big enough to matter in a clinical or behavioral sense? And the answer would definitely be yes, because the 0.02 is, what is it? It's about, it's hundreds of times bigger than the other number. So that would, on that basis, sexual orientation would be recognizable because that difference is big enough to matter. And yet we're also saying in the idea of recognizable subpopulation, if we're really saying that the only thing that matters is gay or not gay, that all of the people who are gay have the same probability of being HIV positive, and that's probably not true either. We need to bring in other variables. So it's a little bit like stratifying on multiple variables at once until you get down to a cell in which everybody's pretty much the same. That's the idea of recognizable subpopulation. Whereas if we looked on something like hair color, here are the redheaded people over here, and here's everybody else, and maybe the redheaded people have a HIV prevalence of 0.010 and everybody else 0.011, that difference is not big enough to matter about. And so we would say that hair color is not part of the definition of a recognizable subpopulation, whereas sexual orientation is. So here, this guy, the recognizable subpopulation for this patient might consist of everybody who matches him on gender, and on age, perhaps broken down into 5-year age categories, and sexual orientation. We might use those 3 predictor variables or covariates or whatever features, whatever you want to call them, to define the recognizable subpopulation. And the important thing to note here is that this is a modeling choice based on judgment. And different reasonable people might make different choices about the variables that define the recognizable subpopulation. So basically for this reason, this is essentially the fundamental reason why probability modeling in the real world is inherently subjective, and I'll have more to say about that in a few pages. Now once we've defined this recognizable subpopulation, we can get the probability. As a person reasoning in the classical approach, you would do the following things. You would establish equipossibility amongst all the people within this guy's recognizable subpopulation. Those are the elemental outcomes, each individual person in there. And then you would count how many of them are HIV positive and how many of them there are altogether and take the ratio. So having defined the recognizable subpopulation, we can get a classical probability for it. And it's just that ratio of integers. Now, as a frequentist, we have to make a dodge because, strictly speaking, the frequentist probability he is HIV positive is undefined because he either is or he isn't. And no matter what repeatable story you're going to tell, throughout those repetitions, he's always going to be just HIV positive or not. So strictly speaking, the frequentist probability of him being HIV positive is undefined, but there's a little dodge, a little trick that frequentists use. Here's how it goes. You equate the probability you're interested in to the following probability, namely that a person chosen at random from this recognizable subpopulation would be HIV positive. So you imagine the process of repeatedly choosing one person at random from that recognizable subpopulation, and you ask what's the limiting relative frequency with which you would get an HIV positive person. That's not quite the same as the probability that he's HIV positive, but it's close. And so that's the frequentist story that you would try. And actually it turns out that the limiting value of that relative frequency would be, of course, the same answer that you got from the classical approach. And as I said, strictly speaking, you're not allowed to talk about the probability that he is HIV positive because he either is or he isn't. But that little dodge is a way to get around that. In the frequency story, you're really only allowed to talk about the process of repeatedly doing something. You're not allowed to talk about what happens on any one particular repetition. Now, as a Bayesian, you would do something different. The fact that you've defined this recognizable subpopulation, you would regard your uncertainty about all the people in the recognizable subpopulation as similar. Like I said, within that little group there, everybody has approximately the same propensity to be HIV positive, and you would regard your uncertainty about the HIV status of every single person in there as similar to each other. And De Finetti invented the actual mathematical word for that. He called it your uncertainty is exchangeable across all the people in that recognizable subpopulation. It just means informally that you judge yourself equally uncertain about HIV positivity for all the patients in his recognizable subpopulation, and then it turns out that this judgment, together with the axioms of what, as I said before, De Finetti called coherence, would also yield the same number from the Bayesian point of view. So I'll talk more about exchangeability and coherence later on. The one thing to note is that you get the same answer with all 3 approaches to probability, but the other thing to note, which is good, the other thing to note, though, is that the way you think about the meaning of the probability is utterly different in the 3 approaches. Sometimes we can use that fact that we sometimes get the same answer in different probability paradigms to our advantage. For example, we will come into situations during this course in which the Bayesian approach to coming up with a probability assessment is quite difficult, and the frequentist approach is much simpler computationally. And we expect, for reasons that I'll show you, that we're going to get more or less the same answer. And so you can use the frequentist calculation as a shortcut, as a Bayesian approximation. So sometimes we'll take advantage of that. That's a very useful thing. Now, what's going on here is that in the frequentist story, the probability assessment describes the process of observing a repeatable event, whereas Bayesian probability is all about quantifying your uncertainty based upon your information base about a true-false proposition whose truth status is unknown to you, whether that story that you're interested in is repeatable or not. So the Bayesian story works for anything, whether it's repeatable or not. Now, let's talk about this business of so-called objectivity and subjectivity. So as I mentioned, Mr. Venn invented this idea of scientific objectivity in the 1870s. And it's very much arises as a consequence of the times in which he lived. He was a scientist working in the late Victorian period in England, which was the period in which England was top nation in the whole world. They had the British Empire. It was practically the absolute apex of the British Empire at that time. And they, as a society, thinking of themselves as the best people on the planet, they went through a process of trying to make everything as rational as possible. And so he wanted to rationalize science, and he wanted to try to stamp out the role of judgment in probability. And so he claimed that it was possible to create a kind of objectivity in probability, and the only way to do it was the frequency approach. Those were his claims. He wrote a book about this that actually greatly influenced Mr. Fisher, whose name will come up a lot as we go along. I've shown you by the very definition that the Bayesian approach is clearly subjective, and unabashedly so, because it explicitly acknowledges the role of information and assumptions and judgment, which are all three crucial parts of the process of uncertainty assessment. Mr. Venn tried to pretend that assumptions and judgment were not part of the probability assessment process, and of course he was wrong in trying to pretend that. What he was trying for is a sort of a standard that's unattainable. My argument is that in interesting applied problems of realistic complexity, the judgment of equivalence or similarity that gave rise to that recognizable subpopulation and is therefore central to all three theories of probability makes them all subjective in practice. And they have different names in each one. In the classical approach, it's the concept of equipossibility. In the frequentist approach, it's the concept of what's called independent and identically distributed sampling from a population, abbreviated IID for independent identically distributed. And in the Bayesian approach, it's the concept of exchangeability. Now, here's an example. So imagine that you were given, everyone in the room, independently given the same data set on HIV prevalence in a large group of people, along with many variables that would serve as possible predictors that might or might not be relevant to identifying the recognizable subpopulations. And I bet there's people in the room who have done an exercise like this in their work. You would basically have a data set that looks like this. You'd have n individuals where n is really huge, and your outcome variable y would be a 1 or a 0, yes or no, about whether the person was HIV positive or not. And you'd have a large number of predictor variables, x1 through xk. And a standard statistical technique, the 1 is HIV positive and 0 not, and the standard statistical technique for working with this sort of data set is called logistic regression. And there's various machine learning ways to work with data sets like this and so on. I'm going to talk about it from the point of view of logistic regression. It's essentially a regression technique. Many of you are probably familiar with the idea of linear regression methods, except that you can't use linear regression methods here because the outcome variable y is dichotomous rather than living continuously on the real number line. So it's a kind of generalization of the ordinary idea of regression to situations where the outcome variable is a dichotomy instead of living continuously on the line. And so here are some of the things that you are faced with as an analyst using statistical methods in this setting. And anybody who's built one of these logistic regression models, you'll be shaking your heads, nodding yes as you hear me say this. Firstly, you have to decide what subset of those x1 through xk are appropriate to include in the model. So some of them turn out to be not that useful as predictors, and some are useful, and you have to choose. It's a kind of subset selection problem, as they call it. Actually, even before that, you have to decide on what scale to express the x's. Should you take, some of them are continuous, should you take the logarithm of some of them to make the distribution look more like a normal distribution, for example? Should you do some other transformation of the x's before you even begin trying to select among them? Then you do use what's called a variable selection technique to figure out what subset is you're going to work with. Then you have to worry about the possibility that the x's enter into the prediction of y in a nonlinear fashion. So you have to think about bringing in quadratic or cubic terms, and also you have to think about bringing in interaction terms amongst these x's. All of this stuff is modeling decisions that you have to make. And if every single person in the room tried to make those decisions using what are called so-called objective frequentist methods for making all those choices, I guarantee you that with about 70 people in the room, when we're done, we would come up with about 30 or 40 different models. Everybody's trying to be as objective as they can be using one or another of these standard techniques. We're not all going to get the same model. We are therefore not all going to get the same probabilities of HIV positivity for any one particular person in this data set, or indeed someone else who comes along. So Mr. Ven's idea is not possible to attain. Well, let's see. I don't regard it as a flaw. Maybe what you're talking about is some sort of idealized human who can do things that the rest of us can't do. And in that sense, maybe we could regard Mr. Ven's, what he hoped for, as something that people call normative rather than descriptive. So normative is some kind of ideal that we would try to reach toward. And descriptive is what we actually do and often end up falling short of that goal. That would be okay with me, except the problem is that no one who's ever been born as a human being and grown up to be a scientist has ever been able to achieve Mr. Ven's goal. That's the basic point. And my point here is that in good faith, with all of us trying to use these so-called objective methods that the frequentists have developed over the last 100 years, each of us might end up using a slightly different method for variable selection. Each of us might use a slightly different method for deciding whether quadratic and cubic terms are necessary, and interactions and transformations and all of that stuff. And we're all using so-called objective methods, and yet we end up with a subjective answer because we end up with different models, and those models lead to different probabilities. So basically what's going on here is that Mr. Ven's goal is actually unattainable. You and other reasonable people might well differ in your judgments on all of those different modeling choices that I just mentioned. So the assessment of complicated probabilities in real life with us, rather than some kind of idealized superhumans, is inherently subjective. There are judgment calls built into probabilistic and statistical analysis, and there always have to be, the same way there are judgment calls built into in all aspects of science. And so that means that Mr. Venn was actually, he was chasing an unattainable goal. And so attention, in my view, should shift away from trying to achieve something that we can't achieve toward the following two things. Firstly, the explicit statement of all the assumptions and judgments that you make on the way to your probability assessments so that other people can think about whether they're plausible or not. And secondly, a vigorous sensitivity analysis in which you you explore the mapping from assumptions to conclusions by altering those assumptions and judgments and seeing how much the altering of them matters. So you perform repeated analyses on the same data set using different methods to arrive at an answer. And if you discover a certain kind of stability, all the roads are leading to Rome, then you've come as close as you can as a human being to the kind of objectivity that Mr. Venn was trying for. And as I said before, to Bayesians, saying that a particular Bayesian probability is objective just means that lots of people more or less agree on its value. In that little example with the 1 and the 2 and the 9 in the little hypothetical population and choosing one number at random, everybody, Bayesian or frequentist or classical or whatever, everybody, if you really spot yourself correctly, the idea of at random would agree on 2/3 as the probability that you'd get an odd number, for example. So that's an example of an objective probability assessment. But in real life, the assumption at random is an assumption. I don't know if any of you have ever spent money on the California lottery, but it's true. Don't they? If you ever watched how they do it, isn't it one of these things where there's a container, a plastic container, and it has a bunch of balls in it, right? And they move the balls all around. And they pick the balls. Is that how it's done? You ever watched the show when they're doing it? We are all hoping it's true that the choice of those balls is, quote, at random, so that every single subset of however many balls they choose is equipossible, has the same chance of being chosen as any other subset. But is it a physical property of that particular machine that makes them equipossible? In fact, no. It's a judgment on our part that they are close enough to equipossible that we're comfortable betting as if they were equipossible for the purpose of setting our betting odds. And indeed, there have been examples in the past, I think it was in the Pennsylvania state lottery about 20 years ago, where people rigged the lottery by going in. They were ping pong balls in those days with numbers on them, by going in and injecting a little bit of fluid into some of the ping pong balls that made them heavier. And then they were able to rig the drawing in their favor and bet on the outcomes that had the heavier balls. So everybody else made the judgment of equipossibility that day, and yet it turned out to be a flawed judgment. So these things are not inherent properties of the world around us. They are judgments on our part about how the world works. All right, let's get back to my case study. Suppose that with this patient's values of relevant demographic variables, we look in the medical literature and find that the background prevalence of HIV for people like him, estimated from the medical literature, is about 1%. The background prevalence, P of A, the probability that he's HIV positive, not yet knowing anything about a blood test on him, turns out to be 1%. So blessedly, in people around him, in people like him, people similar to him, the proportion of people who are HIV positive is blessedly small. Now, of course, that's an uncertainty assessment that is not particular to him, except to say that we look at the group of people who are similar to him and we find that about 1% of them have HIV. Let's try to do better than that by taking a blood test on him. So to improve this estimate, let's say we decide to draw some blood and get a result from ELISA. I'm not going to talk about Western blot yet. Let's just talk about ELISA. Now, suppose the test comes back positive. The question now becomes, what is your updated probability that that true-false statement, A, that the guy really is HIV positive, what's your updated probability that that true-false statement is true? Bayesian probability has that name because the simple updating rule that Mr. Bayes developed, well, he was the first guy to do it, and the way he did it was amazingly simple. He essentially got his name to go down. His name has gone down in history and will always be talked about as long as anybody on this particular planet ever thinks about probability. For one thing, he created the definition of conditional probability, which was a concept that Pascal and Fermat had not thought about because it didn't come up in their gambling calculations. And what we now call Bayes' theorem for propositions is a direct consequence of that definition of conditional probability. So let me take a little break and remind you of the basic facts of probability over on the handwritten stuff for a few minutes. And in doing this, I'm going to go back and forth between various intuitions. I will sometimes appeal to frequentist intuitions, and I will sometimes appeal to classical intuitions. Strictly speaking, if you ever study the frequentist approach, the thing that's inside the probability symbols, the A, in Kolmogorov's way of looking at the world, is supposed to be a set. And so probability for Mr. Kolmogorov is an operation. It's a function that takes sets as its argument and creates numbers that are between 0 and 1. For the Laplace and Bayes and Ed Jaynes and Richard Cox approach, the one I favor, instead, the thing that goes inside the probability symbol is always a true-false proposition. And you can think about the world either way. The true-false proposition way is actually a little bit more general. And so sometimes we'll talk about this as if it were a set. Sometimes we'll talk about it as if it were a true-false proposition. And there won't be much harm in that going back and forth between them. Well, we all know if we were trying to think about the world in a relative frequency way, that if this is supposed to be the relative frequency with which something happens, then it always has to be between 0 and 1, 0% and 100%, with 1 standing for certainty that the proposition is true, and 0 for certainly false, a kind of impossibility. And the reason that Venn invented Venn diagrams was actually to think about probability problems. And so the heuristic that we often use is to imagine that you're throwing a dart at a rectangular dartboard, and it has the following property. The throwing process has the following two properties. Firstly, the dart has to fall in there somewhere, has to fall inside the rectangle somewhere. And secondly, every point at which it could land is equipossible. They're all equally likely to be the place the dart lands. With that frequentist intuition, the probability that the dart falls inside a blob called A would then just be the relative area of the blob of A in relation to the area of the box. And because the dart has to fall inside the box somewhere, we can call the area of the whole box 1, because that represents the truth that the dart has to fall somewhere. So basically, think of the rectangle as having area 1, and then the probability of the dart falling inside A is the ratio, is the area of that blob A divided by 1. People basically, Bayes was the guy who invented the rule for combining two propositions with the AND operation. What's the chance that both proposition A and proposition B are true for two separate propositions? Well, to do that, he invented the definition of conditional probability. He said to himself, if I wanted to know what the probability of B was, it's like comparing the area of B to the area of the whole box. But now instead, suppose I wanted to work out the chance that B is true, given that I know that the dart fell inside A. Then the relevant part of the box that we should be looking at is no longer the whole box, but just the part for A, right? Because we're told that the dart fell inside A. So I'm going to use the notation B bar A to stand for B given A. So given that the dart fell inside A, the relevant denominator now becomes the blob for A, and the numerator becomes the places when the dart falls not only in A, but also in B, and so it becomes the overlap. And so the definition of conditional probability is that the probability that B is true, given that A is true, is the ratio of two things, the probability that they're both true divided by the probability of the thing that you're conditioning on. That's what Bayes did. He invented that. That's all he really did. And then Bayes' theorem turns out to be a simple corollary of that definition. By the way, he also then showed us how to do the work with the AND, because now if I multiply both sides of that by P of A, I get what's called the product rule. This is a kind of chain rule. You know about a chain rule in calculus. This is a sort of chain rule for probability. The chance that two propositions are both simultaneously true can be computed first by working out the chance of one of them and multiplying it by the chance of the second one, given that the first one was true. And you can do it in either order, right? You can go B, then A given B, or A and B given A. And of course, we have a simple rule for working with OR also. If A and B are two blobs and there's no overlap between them, then clearly the chance of A or B is just the sum of those two separate chances. But if there is an overlap and we try to add them together, that creates a number that's too big because we double counted the overlap. So to make it right, we have to subtract off the overlap. So that's the general rule for working with OR, with two things at a time, and you can generalize that readily. This rule for AND, by the way, a minute ago, that also generalizes readily. Go even farther here so I can actually get this on. That's interesting. The probability A and B and C, you do the same thing, you just chain along. You could go A times B given A times C given A and B and so on, just chain along. It generalizes in that way as well. Now, Mr. Bayes, in inventing Bayes' theorem, the narrative behind his theorem is actually really interesting. He wanted to create a story in which he was going to use probability to study the relationship between causes and effects. He was one of the first people to think seriously about cause and effect, which prior to his work mathematically was a realm that was looked at only by philosophers. Up until Mr. Bayes, the notion of causality that everybody had in the world was something that I'm going to call deterministic causality. If I go up on the roof of my house with a hammer and I stand carefully at the edge of the roof and hold the hammer out like this and cause it to let go, it always falls down. It never hovers in the air. It never goes up. It always falls down. So I have caused the hammer to unattach itself from my hand, and the effect is that it always goes down. That's an example of deterministic causality. Every time I do it, the same thing always happens. Now, Mr. Bayes realized that when we were talking about trying to learn things about human beings, for instance, it would be better if we had a more general form, a more subtle form of causality that I would call probabilistic causality. For example, You go into a village back in the 1730s, and some people are dying, and you're a kind of amateur or nascent epidemiologist. They didn't even have that word in those days, but you're trying to figure out why. Are they dying because the water in the well is bad? Are they dying because they've eaten food that was rotten or poisoned? Or are they dying because they've been breathing in some fumes from somebody's tannery or some horrible thing, and they're getting really noxious fumes? So the effect is that some people die and some don't, and the causes are multiple. The possible causes are multiple. It might have been the water or the food or the air or other things as well. And the thing that he realized that was much more subtle than deterministic causality is that you can develop a theory of causality in which it isn't true that everybody dies who drinks the water from the well. It's just that drinking the water from the well increases your chance of dying. And so that's a much subtler form of causality in which there are other forces at work besides the water in the well, and we don't have to say what they are, but we can use probability to quantify how much your chance of a bad thing happening increases as a result of a particular possible cause. So he wanted to talk about cause and effect in a probabilistic manner. He was the first person in history, to my knowledge, to ever think about causality in a probabilistic manner. And he noticed that if you knew what the cause was, so if the cause thing was over on the right-hand side of the conditioning bar, if you could condition on the cause, then it's relatively easy to say what the effects are of particular causes. If you cause the water in the well to be poisoned, really with a strong dose of poison, the effect is deterministically everybody who drinks the water is going to die. So it's actually pretty easy to talk about probability of effect given cause, but it's much harder to do it the other order, to reverse the order of conditioning. If all you see in the world is a particular effect, that some people have died, and you want to work out probabilistically which of the causes of that effect is the most plausible one, that's the second thing down there, the probability of cause given effect, and that's harder. So that was his line of reasoning. And so in order to solve that problem, he realized he had to figure out what was the relationship between those two things. And in our jargon today, we'd say he needed to reverse the order of conditioning. He wanted to go from P of A given B to P of B given A. And what's going on here maps directly onto Mr. Bayes' way of looking at the world. A represents the unknown thing for us, the true HIV status of this patient. That acts like the cause. And D represents the data that we have on this guy, and that, in this case, is the ELISA result, and that represents the effect. If the guy really is HIV positive, then that will have an effect in the sense that ELISA will be more likely to say he's HIV positive. So that's a direct mapping between our HIV case study on the one hand and Mr. Bayes' way of thinking about things. So he wanted to know how the probability of A given D relates to the probability of D given A. So he used this definition. And he had the wit to realize that he could use his definition twice. So he wrote down his definition in the order A given D, and he wrote down his definition in the order D given A. And he wanted to relate them to each other. So he multiplied both sides of the top equation by that denominator, P of D, and he multiplied both sides of the second equation by P of A, the denominator, and he got the following two sets of equations. And then he noticed a cool thing. The chance of A and D both being true is the same as the chance of D and A both being true. Therefore, these two things have to be equal to each other. And therefore, if I divide this expression by P of D, I will have probability of A given D expressed in terms of probability D given A. So there's Bayes' theorem for you, right there. I would call that a sort of nice work if you can get it. Something that looks that simple to us now created immortality for this man. Really, really classic example of low-hanging fruit, right? I mean, he invented the definition of conditional probability, and then it's an absolutely 3-second corollary of that Bayes' theorem. It says, here's how you combine uncertainty. This is your information before the data arrives. This is the data information. This turns out just to be a normalizing constant, and this tells you how to get from the information before the data arrived to the information afterwards. And it all comes out of that definition of conditional probability. That refers to a kind of temporal dichotomy. We can imagine a timeline going along, and the world is split into the information you have about the thing unknown to you before the data set arrives and the information afterwards. And the Latin for before is a priori, and so people call the stuff on the left-hand side of the data your prior information, and that's indicated by P of A in this problem here, the probability of the unknown. And then once the data have arrived, you want to combine the information you had before the data arrived with the data information to get the information afterwards. And the Latin for that is a posteriori. So the information on the other side is called the posterior information. And it evidently stands for the probability of unknown given data. And in the, I see I should have written this in, that in turn corresponds to P of A given D. Problem here. So you want to update, using Bayes' idea, you want to update the information you had before, P of A, to your new information, P of A given D, in light of how the ELISA test came out. And look, that theorem there, that little teeny theorem says how to do it. You take the P of A, you multiply it by P of D given A, you divide by P of D, and you get what you want. So in our problem, we start with wanting to know A given D, the chance the guy really is HIV positive given ELISA said he was, and that's the product of the prior probability he was HIV positive, which is 1% from the medical literature, times this thing here. This is an interesting object. It says the probability that ELISA would come out positive if someone's blood really were HIV positive. Would you like that number to be big or small or in between? The conditional probability that ELISA says the blood is HIV positive, given that it really is HIV positive. You'd like that number to be what? Big, close to 1. That's called, in screening tests, that's called the sensitivity of the screening test. And in 1986, when this case study unfolded, the sensitivity of ELISA was 0.95. Now this thing, this P of D in the denominator, it's as we'll see after the break, we'll take our next break now, this thing is called the normalizing constant, it turns out. It's just stuck in there to make sure that everything adds up to 1 on the left-hand side of the equal sign, because everything has to add up to 1 if you add up across all possibilities. And as we're going to see, it could be given the nickname, it could be called the annoying normalizing constant, because it's very much the hardest thing to compute in all of this stuff. And there are actually several different ways to compute it, including the cool idea of getting what we want on the left-hand side by not even computing it at all. It turns out that we can actually avoid having to compute it. It's the hardest thing to compute, so let's see if we can figure out how not to have to compute it. All right, let me get back to my narrative here in the notes. So there's Bayes' theorem for propositions. A and D are both true-false propositions. And it says the posterior probability, that's the language people use, the posterior probability that A is true given that D is true can be computed by multiplying two things and dividing by another. The prior probability that A is true times something that in this context is called the sensitivity, but in general would be called the sampling information, and also it would be called the likelihood. And so basically, those of you who have heard about maximum likelihood before, that's where the likelihood story comes in. So you multiply the prior information times the likelihood information and divide through by the normalizing constant, and that gives you the posterior information that you want. And so here, A stands for the unknown, here the truth value of the proposition that the guy's HIV positive, and D is data. And so we find posterior information, probability of unknown given data, is a constant, normalizing constant, times the prior information times the likelihood information, which represents the probability that the data would come out in a particular way if you knew what the unknown thing was. And as I mentioned before, the prior and posterior terms emphasize the sequential nature of human learning. Strictly speaking, they're not very good names, because actually the thing that's called the prior is supposed to stand for all of your information about the unknown external to the data set. Whether you got that information before or after the data set arrived, it doesn't matter. This is supposed to represent your information about the unknown external to the data set. This is supposed to represent your information about the unknown internal to the data set. That's the dichotomy that really matters. Information internal to the data set, information external to it. But we are stuck with these names prior and posterior because people have been using them for more than 50 years, and so I'll just go with that as well. And so the theorem says update multiplicatively on the probability scale by multiplying your prior information by the likelihood information and renormalize, and out comes the thing you want. And so let's take our second break. We had to cut into things a little because start a bit late, so I'll start once again at 11:30, 10 minutes from now roughly, to get back on schedule. there actually turn out to be 3 different ways to solve this problem, the final computational challenge here. We have to either figure out how to compute P of D, normalizing constant, or we have to figure out how to do something clever so that we don't have to compute it. And there are 3 different ways to solve this problem, all 3 of which are illuminating for how we're going to go from here. Let me show you the first way, and it goes like this. Let's imagine building a little 2x2 contingency table, as people call it, in which we imagine running a large number of blood samples from people who are like this guy through the ELISA machinery. And we count how many people fall into each of these different cells. And we cross-tabulate each blood sample against 2 things. In one dimension, we keep track of what ELISA says. Either ELISA claims the blood is HIV positive or not, which we've agreed to call D for ELISA says HIV positive and not D for not. And we cross-tabulate that against the truth. So we've got A for HIV positive as truth and not A for HIV negative as truth. And we imagine running a large number of blood samples, let's say 10,000, through that story and see what happens. So the idea behind a contingency table is that we're going to count how many of the different blood samples fall into each of those cells. And when we complete this table, we're going to be able to compute any probabilities that we want. Any conditional probabilities we're interested in will be computable from the table. The way you interpret the entries in the table, for example, this cell right here represents probability of A and D. This cell over here represents D together with A plus D together with not A, so it represents the chance of D by itself. And in fact, that's the annoying number we're trying to work out. That number divided by 10,000 will give us the value for the chance of D. Similarly, this number here tells us about the probability of A. We work out the number right there and divide it by 10,000 to get the probability of A in a relative frequency sense and so on. So I'm appealing to a relative frequency and classical probability sort of definition here. All different roads are going to lead to Rome in this problem. All right, so I want to use the facts I know about ELISA to solve this problem. Not only ELISA, but also this guy. And so the first fact we know about him is that the background prevalence of HIV among people like him is 1%. The second fact we know about ELISA is that we worked out what sensitivity was. And I should have told you how they do this. Basically, they take a bunch of blood samples that are known to be HIV positive, and they pass them through ELISA. And because ELISA is a screening test which is based upon, that includes the concept of measurement error in it, sometimes it gets the right answer and sometimes it doesn't. And the way they actually do it, by the way, is ELISA is trying to pick up antibodies in the blood against the, let's see down here. ELISA is trying to pick up antibodies in the blood for the human immunodeficiency virus. And they pick a particular cut point along that antibody scale. And if the antibodies register above that cut point C, then ELISA announces HIV positive and otherwise HIV negative. And ELISA's measurement of the antibodies is subject to measurement error, so sometimes it gets the wrong answer. And we've already seen that ELISA in 1986 had what looked like a pretty good sensitivity number. But once you've got the idea of running a bunch of blood samples that are HIV positive through ELISA and seeing how often it gets the right answer, there's another thing you'd need to do as well, which is to run a bunch of blood samples that are HIV negative through ELISA and see how often it gets the right answer for that. And so that would be like saying, given that the blood is not HIV positive, what's the chance that ELISA says the person isn't HIV positive? And that's a completely different number, of course. That has another name in the world of diagnostic screening. It's called the specificity of ELISA. And in this case, in the 1980s, that number was even better. It was 0.98. Again, that's a number, for the same reason you guys said before, we'd like that number to be big, close to 1, and because it's a success rate for ELISA, and it is even closer to 1 than before. So to summarize, ELISA looks pretty good. The sensitivity is 95%, the specificity is 98%, and what we want to work out is what's the chance that the guy really is HIV positive, given that that ELISA says he's HIV positive. And if ELIZA's any good, you would expect this number to be what? To be big or small or in between. If ELIZA's any good and ELIZA says the guy's HIV positive, then the chance he really is should be big, right? Close to 1. Expect to be big. Close to 1. Well, we're in for surprise. So let's see how the surprise unfolds. We want to use each of those 3 facts to fill in the table there somehow. And it turns out that the prevalence is the easiest one to use first because it's the one that's the unconditional probability in the whole story. So how can we use the prevalence to fill in any of the numbers in that table? I have a total of 1, 2, 3, 4, 5, 6, 7, 8, 9 integers I want to fill in, and I know one of them already. The total is 10,000. How can I use the 0.01 to fill in the probability of A, which would be like filling in that number there? What should I do? Take 1% of 10,000, which is 100. So that number goes right there. We can work that out. That comes directly from the prevalence. And can I fill in any of the other numbers now? If that number's 100, then this number has to be what? 9,900. So the column margins of the table, as people call it, come directly from the prevalence. Can I use the prevalence information to get anything else in the table, or have I exhausted its usefulness? The prevalence information. It can't help me any farther. All right, let's look at the sensitivity and see how it might be able to help. It says, among those occasions when the blood really is HIV positive. So that's like focusing on what in the table? A particular row in the table, or a particular column in the table, or a particular cell in the table. On those occasions when the blood really is HIV positive. That's like focusing on the first column, right? And so on those 100 occasions when the blood really is HIV positive, how often does ELIZA get it right? 95%. So I get to put a 95 right there, and by subtraction, a 5 right there. So the sensitivity information gives us that number there and that number there. And then similarly, the specificity information should give us these 2 numbers here. So on those occasions when the blood is not HIV positive, that's like conditioning on the second column, 98% of the time we get the right answer. So you have to work out 98% of 9,900. That turns out on your pocket calculator to be 9702. And then by subtraction, this number has to be 198. And now we're done. These 2 numbers, the 9702 and the 198, came from the specificity information. And now having filled in the whole table, I can get the margins. So 95 plus 198 is 293. Did I do that right? And this becomes 9707, and those 2 numbers had better add up to 10,000, and it looks like they do. We have now computed the denominator by this trick of thinking about a large number of blood samples and using the prevalence to define the column totals, using the sensitivity to define the first column entries, and using the specificity to define the second column entries. And then we were able to use simple addition to work out the thing we want. So here we go. We're now able to compute the thing that we're interested in. Let's do it. Probability of A given D, according to Bayes' theorem, probability of A, probability of D given A over probability of D. P of A is 0.01. P of D given A is 0.95. And P of D turns out to be 0.0293, because this is only 293 out of 10,000. And when you do that calculation, you get a big surprise. It comes out only about 1/3. You see it now, finally. Yeah. Another idea would be to move this thing this way a little bit, and then I can get everything I want. Right. Okay. So a pretty interesting thing has just happened. We expected this probability to be large, and it actually comes out rather small. In a minute, we're going to figure out why, but I'd like to take a minute to show you the other 2 ways to work this probability out, one of which is a lot easier than what we just did, and the other which is actually about equally difficult to the way we just did it. So let me see here. In fact, another way, by the way, the other way we could have computed this number, the thing we want, P of A given D, in this table, is we could have said, well, if you know for sure that ELISA says HIV positive, that's like conditioning on the first row, and so the relevant denominator there is 293. And then of those 293 times, ELISA says it really is HIV positive 95 of those times. And that's a simple way to see directly that the answer is only about a third, because basically we have 100 over 300 roughly. So the second way to see what's going on is to be what a friend of mine used to call, let's try to be creatively lazy. I used to work at the Rand Corporation, and I had a friend there named Bill Rogers. If any of you have ever used the statistical computing package Stata, he was the one who invented Stata. He left Rand to go on to build the Stata empire. And when we would be in meetings with statisticians and economists and health policy analysts and blah, blah, trying to figure out what to do about something, and the problem was difficult, we would be knocking our head against the wall, and Bill would say, let's see if we can figure out how to be creatively lazy. And what he meant was, is there some way to do an end run around the problem? Can we reformulate things so that something simpler happens? And there is a way to be creatively lazy here. We want to not calculate P of D. That's the version of being creatively lazy. And so here's the trick. You write down Bayes' theorem for A given D, and you also write it down for not A given D. And what simple thing can we do with those two formulas now so that we don't have to calculate the thing we don't want to calculate? Just divide them, one from another. And the thing we don't want to calculate will disappear. The left-hand side will be the probability of A given D divided by the probability not A given D. But look, that's what earlier we called an odds ratio, the odds. This part's called the posterior odds. Then the right-hand side will be the product of two things that look like odds as well. The first one will be P of A over P of not A. That's the prior odds in favor of HIV positivity. And the second thing is something that people call, since both of these are likelihoods, they call it the likelihood ratio, and the other name for it is the Bayes factor. And so what results is this expression here, and that in turn in words, posterior odds equals prior odds times 3, actually 3 different names. Sometimes called the likelihood ratio, sometimes called the Bayes factor, sometimes you could call it the data odds. So the posterior odds are like the product of the prior odds times the data odds. You could think of it that way. But I'm going to use the word Bayes factor. And we'll have more to say about Bayes factors in more complicated problems way later in the course, somewhere around week 7 or 8 probably we'll talk more about Bayes factors. Now, what are the computations? How does it go? I think that I can go back to the screen for that. Writing Bayes' theorem in odds form, we get that guy right there. We have the sensitivity and the specificity. We plug them in, and we find that the Bayes factor turns out to be sensitivity over 1 minus specificity, which is 0.95 over 0.02. Because remember, specificity was not A given not D, and the thing we want down here, or rather not D given not A, and what we want D given A, so it's 1 minus it. So that becomes sensitivity over 1 minus specificity. And that becomes a Bayes factor, or likelihood ratio, of 47.5 to 1. So basically the data is saying 47.5 to 1 odds in favor of the guy being HIV positive, arising from the fact that ELISA said he was HIV positive. So that seems like pretty strong data odds in favor of his HIV positivity. But remember that he came from, thank goodness for him, he came from a background population where the prevalence of HIV was quite low. The prior odds are actually 99 to 1 against him being HIV positive. And you combine those odds multiplicatively, 99 to 1 against times 47.5 to 1 in favor, and you get 2-to-1 odds against when you're done. And therefore, the probability he really is HIV positive is only about 1/3. The third way to make the calculation is to go right at it. And it's using a technique that we'll use later on in the class. It's our first example of what I'm going to call mixture modeling. And it's also our, yes, please. Which things are you contemplating adding? So are any of those three quantities in that expression there? Are you thinking about adding anything there, or what? Something else? Yes. Yes. I like where you're headed. That's exactly right. The point is that if you want to work out the chance of the data coming out the way it did, the only way to work that out is to bring in the information about whether the person is HIV positive or not. So let me go through that. I think what you're doing is leading me into exactly the thing I wanted to show you guys next. So let's do that. So here I have a little Venn diagram that helps to see what's going on, and some symbols that go along with it. So P of D here is the probability that ELISA did come out positive. And what we'll notice repeatedly in making Bayesian calculations is that when we want to work out something that's hard and we find that we can't work it out directly, we can make the calculation easier by bringing something else into the conversation that makes the task easier. And so there are two dimensions of information in this problem, namely the truth about whether the person's HIV positive or not on the one hand, and also what ELISA says. And here we're trying to make a probability calculation about what ELISA says. It would be a lot easier if we knew what the truth was, because then we'd have those sensitivity and specificity pieces of information to help us. So in a trick that you may have learned in your original probability classes called the law of total probability, I'm going to take the blob for D, and I'm going to put over top of it a breaking down of the entire story into a series of subsets that have the following two properties. They're mutually exclusive. In other words, A and not A cannot possibly be true at the same time, and they're also exhaustive. Either A has to be true or not A has to be true. That's referred to in set theory as a partition of the story. So we have mutual exclusive story plus exhaustive story. So I superimpose a partition over top of the blob for D. I superimpose a partition with respect to the truth. And now the chance of D being true has to be, by looking at the partition, the sum of the chance of D being true and A also being true, together with the sum of D being true and not A being true. So basically, I bring in the truth by adding over all the possibilities involving the truth. And that, in turn, requires thinking about a partition about all the different ways the truth could be. Now, remember the definition of and. That's equal to the probability of A times D given A. That's A and D. And this guy here is equal to not A times D given not A. And we know all those things. A is 0.01, not A is 0.99. D given A is the sensitivity, and D given not A is 1 minus the specificity. We know all those things, so we can work it out, and we get that same number, 0.0293. This is going to be our first simplest example of something that's later on called mixture modeling. We are mixing over the truth by bringing in the truth and making this calculation here. We're taking a weighted average. We're computing the story for D by taking a weighted average of D given A and D given not A, weighted by the probabilities A and not A. So we're mixing over the truth to get the thing that we want. And that'll be a very valuable tool when we compute predictive distributions, and it will come up in other things as well. And so now finally we make the calculation that we were interested in, and the result is as you've seen. So 3 different ways to get this calculation. Yes, please.
So in real life, though, isn't it?
That's true. That could come directly from the test results, the same way they were doing the sensitivity and specificity. but actually it turns out you don't have to know it. You can derive it from the sensitivity and the specificity. We just
Those seem kind of derived from the original test results, like they
that could be one way. Yeah, that could be one way to think of it. But if you knew P of D, you couldn't work out the sensitivity and specificity from it. But the other way around, if you knew both of those, you can work out P of D as long as you know the prevalence. So. And the other thing about P of D, you'll notice, is that the P of D says it's the rate at which ELISA fires off positive, but not for everybody, just for people who are like this patient, because you also have to know what the background prevalence is in this calculation. See that number right there. And so, in fact, all three of the ingredients, the prevalence and the sensitivity and the specificity, all come into calculating this P of D. It's not a universal number. It doesn't come just from doing ELISA on all blood samples and seeing what that is. This should really be P of D, given that this guy is a guy from the subpopulation of people whose background prevalence is 1%. That'd be a better way to write the definition. So you really do have to actually compute it out this way. Does that make sense? Yeah, uh-huh. This we're going to generalize to an integral later on. That's exactly right. We've now summed over all possibilities for A, and we're going to replace that with an integral later on. That's exactly right.
So if A could have 10,000 values for values, it's very difficult.
That's correct. And he has pointed out another one of the things that was an Achilles heel for Bayes for a long time. We're going to see as soon as we go and try to apply Bayes to unknowns that live continuously on the real line, that sums get replaced by integrals, and we end up with potentially high-dimensional integrals, and the high-dimensional integrals can be extremely difficult. Most of them can't be computed in closed form, and we'll have to invent some approximation methods. In fact, the real thing that held the Bayesian paradigm back for much of the 20th century was that you just couldn't do the computations. Okay, let me collect myself here. So, returning to our main line here, why did ELISA come out this particular way? In fact, we could talk about it with relation to this table as well. Let's go back to this table. The answer came out 95 over 293. We wanted that fraction to be big, and it came out disappointingly small. So when is a fraction big? When the numerator is big, or the denominator is small, or both, right? That's what makes a fraction big. To make it even bigger, we would have either wanted the numerator to be bigger, or we would have wanted the denominator to be smaller. But the numerator can't get much bigger, because it can't be bigger than 100 for people who are like this guy. We can't ever have that number be bigger than 100. It's driven by the prevalence. Conversely, or another aspect of the same phenomenon, why was this 198 so big? It's because we took a huge number, 9,900, which arose because the prevalence was relatively low, and we multiplied it by a number that looked at 1 minus that, which looks pretty low as an error rate, 0.02, but 0.02 of a huge number is a big number. So what's going on here is that the fraction came out disappointingly small because that 198 was so big. Now let's think about the 4 cells of this table. This cell here, the blood really is HIV positive, and ELISA says HIV positive. So the upper left-hand cell, ELISA gets it right. The lower right-hand cell, ELISA gets it right. The 2 off-diagonal cells represent mistakes on ELISA's part. Let's look at the real-world consequences of each of those mistakes, and you can think along with the developers of ELISA, and we can figure out what the solution is here. I have to tell you what ELISA was invented for. The purpose of ELISA, it was invented in order to do reliable blood screening for hospitals and blood banks. They wanted to be able to try with relatively high accuracy to keep HIV-positive blood out of the blood supply for hospitals. So, pardon? That's right, but different ELISAs, it stands for enzyme-linked immunosorbent assay, and so you could use anything that picks up different kinds of antibodies. So this happens to be an HIV ELISA, but there's other ELISAs for other viruses. That's certainly true. So what happens in this cell here? The truth is that the blood is actually okay, and then ELISA says it's bad. What's the real-world consequences? If you're a hospital and you've just run ELISA on it, you throw that unit of blood away. Is that a bad thing? Mildly bad. If you wanted to try to put a dollar value on it, is the United States a country where you could be paid for donating, for giving blood? Do you anybody ever, and do you know a number? Mostly people donate their blood to Red Cross and so on, but there are places you can go and be paid. I think it's on the order of 50 to $100. So you're losing 50 to $100 by throwing away a good unit of blood. What about this cell here? What happens here? The blood really is HIV positive, but ELISA says it's not. What happens now? Someone has surgery, they infuse this blood into them, and it's actually 100% they're getting HIV. That is the most reliable transmission method for HIV, is to get a blood transfusion from someone who's HIV positive. And this is much, much worse. And you remember how I said the people built the HIV story. They have a little constant C, and they shift that constant up and down the number line. As they move C to the right, it becomes harder for ELISA to say HIV positive, but therefore it becomes easier for it to say HIV negative, and conversely. So if you were the person designing ELISA and you could choose that number C, which of these two kind of mistakes would you try to minimize? The cell that has 5 in it or the cell that has 198 in it? The 5 in it. In fact, you would have liked that to be 1 or 0. You'd like that to be really, really small, right? So this is why the later ELISAs are much better. Their sensitivities now are more like 0.997, things like that. So there's hardly anything in that cell at all. What's that? So you're worried about whether the person will reject the new liver, for example? That's interesting. And you saw, because of this caliper here, moving this caliper back and forth, that there's a kind of a beanbag effect. The more I push on one end, it shoves out the other end. If I make HIV positive from ELISA more plausible, then easier to say, then it becomes, the other mistake becomes bigger. So you can't have them both at once. And so the ELISA people were doing a smart thing. They made sure this cell was pretty small, and as a result of the beanbag pushing out the other end, the cell has to be quite big. So why would it have been a bad idea for that congressperson to get his way? It turned out to be a guy. Among people whose background prevalence of HIV is 1%, ELISA, they really, let me say it the other way. Among people like this guy here, the probability the guy really is HIV positive, given that ELISA says he is only 1/3. And so that means that what's going to happen is ELISA is going to create an enormous number of false positives if you run it on everybody. Lots of people who don't have HIV are going to be told they do have HIV. And of course, that would be a terrible thing. You'd be getting many, many people in a sense in which they feel like they're in real trouble. So as it says at the bottom of this page here, ELISA was designed to have a vastly better false negative rate than false positive rate. The false negative rate is the probability of being HIV positive given ELISA says negative. That hardly ever happens in the table. It's only 5 times out of 9707, so it's only about 0.0005 at the time, about 1 time in 2000. The false positive rate is the chance of ELISA saying, of really being HIV negative when ELISA says positive. That's 1 minus the thing we just calculated. That's 2/3. So there'd be a huge false positive rate. And so that's why with the contemporary ELISA that people had in those days, it would have been very stupid to screen every single person in America.
What was the primary purpose for designing ELISA? Like to screen,
it was to keep HIV positive blood out of the blood system, out of the blood bank system. And for that purpose, they were right to make the cell that had the 5 in it as small as they could. And the inevitable consequence of that is the other cell got big, and therefore there were a lot of false positives. If you try really hard to hold down the false negative rate, unless you can come up with a more accurate way to do the assay, you're going to end up with if you try to make the false negative rate really small, you're going to have a high false positive rate. Those of you who studied the Neyman Pearson stuff about hypothesis testing, it's exactly like that business about type 1 and type 2 error. with a fixed sample size, you can't make them both simultaneously as small as you want. As you make one of them bigger, the other one gets smaller and vice versa. Okay. So as we've seen, formalizing the consequences of the two kinds of mistakes here would require you to quantify the costs of different kinds of misclassification. If you were going to try to be more formal about deciding where to draw the line in having ELISA say HIV positive, where to put that cut point C, then you would have to be in the business of formally quantifying the cost of making a false positive and the cost of making a false negative. And that shifts attention in the problem away from science, which is, as I said earlier, the acquisition of knowledge for its own sake. In this problem, we were essentially trying to do inference. We were trying to find out the truth about this guy's HIV status. That's a scientific problem. It shifts the focus away from science on the one hand to decision making on the other hand. For instance, what use of ELISA and Western blot would yield the optimal screening strategy? So you and I can think that through now. Suppose you were allowed to use any combination of ELISA and Western blot you wanted to. ELISA is really good at not making very many false negatives. So here's some possibilities. You could give ELISA to everybody, like this guy, or you could give Western blot to everybody, like this guy. And what would be the consequences of each of those? The good thing about giving ELISA to everybody is what? It's cheap. The bad thing about it is that you'd have a lot of false positives. The good thing about giving Western blot to everybody is it's highly accurate, but the bad thing is it's really expensive. So is there an adaptive strategy? Help me think through this. Try the cheaper one first, right? So let's try ELISA first. In fact, this is what's actually done. If you ask for an HIV test, they split your blood sample into 2 vials, and they run ELISA on the first vial. If ELISA says negative, then what do we conclude? Or what do we do next? If ELISA says negative, then we say the blood is HIV negative, because ELISA is really good at that. But if ELISA says positive, what do? We try again with Western blot on the other one. And that turns out to be the best strategy, and we're about to prove that using decision theory. At least I'm going to show it's better than an ELISA alone strategy, for example. And that's actually what's done today if you wanted to go and have a blood test for HIV. The ELISA today is better than the 1986 ELISA, and the Western blot today is better than that one, but they still use that 2-part strategy. Okay, we have been... Well, indeed, what about those 5 people? What about those 5 units of blood that did get into the blood supply? In fact, I have a very unpleasant story to tell about that. I lived in England and taught at the university in the city of Bath for 8 years before coming to Santa Cruz. And one of my best friends there, in fact, he was my first PhD student in England, is a lovely man from Wales named Ryan Shiel, and he was born with hemophilia. And in approximately 6 months after, to treat hemophilia, you have to be injected with clotting factors, which are derived from human blood. That was the only treatment available in the early 1980s. And so what do you think happened to my friend and all of the people around him as soon as HIV appeared, before we actually knew it was present? There was a period of 3 or 4 years where we couldn't figure out what was going on. What did the British government do to him without meaning to? They gave him HIV. He became HIV positive. They also gave him hepatitis C without meaning to. And so he became one of a cohort of several thousand people who were made HIV positive just by being given bad units of blood as part of their clotting factor. He is now, by the way, he's now one of only 2 of those people still alive from early 1980s to now. And one of the reasons he's still alive, I think, is the following. He is the second most optimistic person I've ever met. It really matters in fighting chronic diseases. And the first most optimistic person I ever met was his mother. And so he had a big advantage of being in a family where his mother basically said to him, don't let this thing beat you, don't quit. And anyway, so you're right. What about those 5 people in that cell? Those people got HIV from in surgeries where they needed infusions of blood. I mean, that's the best they could have done using 1985 technology. That's the deal. Now, I said before that we as a species have been thinking mathematically for 4,000 years. How old is the human species? When did we separate off from other Homo X or Homo Y? Is it Are we 100,000 years old as a species? Anybody know any numbers about 100? So we've been thinking mathematically for 4,000 years. We've been making decisions for 100,000 years. Being alive as a human being requires you to make decisions constantly. And yet it wasn't until the 1920s that anybody started to think intelligently about how to make decisions carefully in the presence of uncertainty. And the guy who figured it out is a brilliant man named Frank Ramsey, who did it while he was still an undergraduate in mathematics at Cambridge University. He did a short series of extraordinarily brilliant and important things and then died of some disease, I forget what. If he had lived, he would certainly have been one of the most influential statisticians and econometricians of the 20th century. He was really, really genius level. He invented the thing we're about to look at. John von Neumann, another very smart man, and Hal Morgenstern made contributions. Also, a Bayesian statistician named Jimmy Savage also made major contributions. So now we want to talk about axiomatic approaches to rational decision making. There are a bunch of different axiomatizations of this. The one I'm going to show you is from another book that it was worth knowing about, just called Bayesian Theory by these guys Bernardo and Smith. That's in the references at the end of this PDF. And so they break things down into the following ingredients. I will show you a simpler version of this story later on, but let's look at this one because it's a good one to think through. You have to start being able to specify a set of available actions. In other words, you have to, later on we're going to call this the action space. You have to be prepared to enumerate all the different choices, things you can choose from. If there's an action that's better than the one you end up deciding on that you forgot to put in your action space, too bad, because you'll never find out it was better because you didn't include it in your action space. So this is a critical ingredient. You have to make your action space as big as it can reasonably be to have a good chance of finding the very best thing to do. Let's call the different actions lowercase a sub I. And then for each action AI, there's a set of uncertain outcomes, let's call them EJ, describing what will happen if you choose action AI. And then following on from those uncertain outcomes, there's a set CJ of consequences corresponding to the outcomes. So an action could be use ELIZA. An uncertain outcome could be whether ELIZA says HIV positive or not. And a consequence could be if ELIZA got it wrong, what are the human and monetary consequences of that happening? So those are the three ingredients we had a minute ago. And then the fourth thing you have to input is a preference relation, which we could describe with the symbol less than or equal to, expressing your preferences between pairs of available actions. So if you say A1 less than or equal to A2, that means A1 is not preferred by you to A2. Or another way to say it is A2 is at least as good, as far as you're concerned, as A1. And then if it goes in both directions, if A1 less than or equal to A2 and also A2 less than or equal to A1, that's like saying you're indifferent between them. So let's use the tilde symbol to stand for A1 and A2 being equivalent, as far as you're concerned. It turns out that this preference relation immediately leads to a qualitative ordering of the uncertain outcomes. And within this framework, it turns out that you have to make further assumptions, which Mr. Savage and Mr. De Finetti called the coherence axioms, to ensure that your actions are internally consistent. And here are these axioms. You have to be prepared to express preferences between simple dichotomies. You have to be able to say, on the basis of the inputs in this theory, do you prefer A or not A for any of the A's that are possible? Then obviously there needs to be a transitivity axiom. If you think that action 2 is better than 1 and 3 is better than 2, then 3 had bloody well better be better than 1, right? So there has to be transitivity. And then there has to be something that Jimmy Savage calls the sure thing principle. If in two situations, no matter how the first comes out, the corresponding outcome in the second is preferable, then of course you should prefer the second situation overall, no matter how the first thing happened. So that's called the sure thing principle. And these coherence axioms turn out to put the comparison relation, less than or equal to, on a sound footing for what you might call qualitative uncertainty assessment, but we don't yet know how to quantify. It's almost like trying to define a system for weighing things, and we've gotten to the point where we can say that one thing weighs more than another, but we can't say by how much more it weighs than another. And to go further, you need one more assumption, which is like the way we solved the weight problem. Did you know that there is still today in Paris under a bell jar a block of metal called the kilogram. There is a piece of metal called the official kilogram. And when you decide how much something weighs, that has been arrived at by an elaborate process of comparison of various things to the official kilogram. That's essentially how scientists decide how much something weighs. And so the way we compare things to each other is we agree on a set of reference weights. So there's an official kilogram. You could imagine an official gram and an official microgram and so on. And you have a whole bunch of those reference weights, and you figure out how much something weighs by comparing it with all those reference points. And you do that similarly with probability. You create a series of idealized situations that are things that you can evaluate numerically, and then compare what you're interested in with those. And so the final axiom guarantees that for each outcome you're interested in, there exists a standard outcome, like asking how often an idealized coin would land heads, how often 2 idealized coins would land heads, how often 4, how often 8, and so on, such that whatever outcome you're thinking of, it's equivalent to one of those standard ones. That's like having the official kilogram, the official gram, the official microgram, and so on. And this has been very abstract, but it turns out that this framework implies both the existence and uniqueness of a Bayesian probability system for you that maps from outcomes to the unit interval and corresponds to the judgments that arise from your definition of preference relation. And you also get out something that the economists and statisticians call a utility function, which is specific to you. And it's going to be a number. It maps from consequences to the real number line and quantifies your preferences. And we could either by fiat, by definition, decide that large utilities are good or small ones are good. It doesn't matter. And by agreement, everybody always defines it so that large utilities are better than small ones. For utility, sometimes you can substitute a word like money, for instance. If you're thinking purely in financial terms, people mostly want more money than less money, and so that's like wanting a higher utility value than a lower one. That's not a very good analogy, though, because in a lot of real decision problems, there is a monetary component and also a non-monetary component. And you have to, in your utility function, you have to be prepared to think about both of those. And here's the hard part. You have to be able to bring the non-monetary component onto the monetary scale. That's the part that makes it hard to do. So this is pretty abstract. Here's 3 concrete results that come directly from this way of trying to make decisions. Firstly, Bayes' original definition of personal probability comes right out of this framework, and it's actually quite a beautiful way to think about how to quantify uncertainty. So let's suppose for the moment that consequences are monetary, and let's say in US dollars, because that's what we all think in. To say that your Bayesian probability of a particular consequence is lowercase p, or rather for an outcome is lowercase p for some uncertain outcome e, whose truth value will be known in the future, is to say that you're indifferent between 2 things. You're indifferent between either you pick a small amount of money, lowercase m, and you're indifferent between receiving p times m dollars for sure, or betting with someone in such a way that you'll get the whole m dollars if e turns out to be true and nothing at all if it's false. So let's think through that in an example. I had my rain example before, for instance. And suppose you were trying to figure out what your personal probability, according to Bayes' definition, is of rain in the next 24 hours with that hypothetical rain gauge on the roof of this building. Let's say you thought it was 0.6. Let's just pick that number to try it on for size. Then that says that you would be indifferent between either receiving $6, let's say m is $10. We pick a relatively small amount of money that you wouldn't mind losing. You're indifferent between receiving $6 for sure or betting with someone in such a way that you'll get the whole $10 if it does rain and nothing if it doesn't. And if you discover that you would prefer one of those options, A or B, to the other one, that's telling you that you haven't chosen the right value of P yet. And according to which one you prefer, you adjust the value of P up or down until you discover that you're approximately indifferent between them. Bayes invented this in around 1730, and it's actually a wonderful way to think about probabilities. You can actually use this to elicit, is the formal verb, you can use this to elicit probabilities from yourself. It's expectation. That's exactly right. And in fact, De Finetti defined an entire axiom system based only on expectation. That's exactly right. Now, why does M have to be chosen small? Suppose M was $1 million. Then if your personal probability of rain was 0.6, would you really be indifferent between receiving $600,000 for sure or betting with someone in such a way that you'll get the whole million if it rains and nothing if it doesn't? Are you really indifferent between those two things? What would you prefer? Take the money and run, right? You take the $600,000. And that's because if you trace out your utility function in money, you'll discover it's not linear in money. It's bowl-shaped down. It looks more like a logarithm function. And so that's why Mr. Bayes, he understood this. Already back in 1730, he said, you have to pick a number m that's small, because otherwise, if it gets p times m gets really big, everybody's going to go with the sure thing. And so you pick a number that's small, and this allows you to actually work out probabilities. Secondly, once you lay down these coherence axioms, all the standard rules of probability come directly out as theorems rather than as things you assume. In the Kolmogorov system, you assume all the usual things, and then you prove theorems about how things work. In this axiomatization, you assume those rationality axioms, and the rules of probability come out as theorems, which is pretty cool. So it first bothered me when I first started hearing about frequentist and Bayesian probability. Do you get different answers in terms of how the probabilities actually manipulate? And the answer is no. Coherent probabilities always live between 0 and 1. And the chance of something not being true is 1 minus the chance of it being true. That's how not works. And the or rule works. And the product rule works for independent outcomes. And the conditional probability general product rule works. It all works fine. There is a little bit of mathematical nicety about in this E1 or ... or EJ, whether you allow the number of things being ORed together in there to be countably infinite instead of only finite. And in fact, De Finetti's approach only guarantees that this works in a situation, in a framework that he calls finite additivity. Capital J has to be finite. And strictly speaking, the Kolmogorov system is based not on finite additivity, but on countable additivity, which is what you get by letting capital J go to infinity. But that turns out not to matter in real applications. And also, conditional probability, of course, has a natural definition in this setup and is the same definition that you know. And if you choose a way to behave that violates those coherence axioms, then the thing I mentioned earlier happens. Someone who is watching your behavior can make Dutch book against you, can point out to you, can offer you a set of bets which are guaranteed to make you lose, no matter what the uncertain thing turns out to be. In my example, whether it rains or not, or whether the guy really is HIV positive or not. And I have a problem in the problem set in which you get to actually think through and figure out how to make a Dutch book. So anybody wants to try, there's a problem in there that asks you to think about how to make a Dutch book and gives you the answer for how to actually do it. So if you want to try this. So the basic story is that coherent Bayesian probability obeys the same laws as with the classical and frequentist approaches, apart from that technical thing about finite versus countable additivity. But none of this so far has said how you should actually make a choice. Now, I said that by convention, large utility values are preferred to small ones. And so it seems like what you would want to do is to pick the action that maximizes your utility. But your utility depends upon uncertain things. And so you can't maximize your utility because it depends on things you don't know the truth about. So what Frank Ramsey proved is a very beautiful and simple result, which is something that you might have thought is intuitively the right way out. Namely, if you can't maximize utility, the best you can do is to maximize expected utility, where in the random variable sense, where the expectation is taken over your posterior distribution, representing how much you know based upon the data that you have and the other information external to the data. And so, given your probability and utility judgments, your decision making is coherent if and only if for each action AI with associated uncertain outcomes EJ and consequences CJ, you compute the expected utility and you choose the action that maximizes the expected utility. So you have the acronym in economics MEU, maximize expected utility, and it's obviously the same acronym, the same idea in statistics as well. And so let's make a calculation, and then that'll finish this stuff before lunch. So here's our HIV screening example again. There are lots of different possible actions, but I'm going to show you how to choose between the following two actions. Action A1, obtain ELISA results at a cost of C1, which is $20, and declare the patient HIV positive if ELISA says positive. Otherwise, declare the patient negative if ELISA says negative. That action is going to have the advantage of being cheap. Now, action 2 is the adaptive action you guys mentioned before. We began by obtaining ELISA for sure at a cost of $20, and then we go on. If ELISA comes out positive, we obtain Western blot at an additional cost of $100, which I'll call C2. And then finally, if Western blot is positive, we conclude that the patient is HIV positive, and if Western blot is negative, we conclude HIV negative. If ELISA came out negative in the first part of this one, we declare HIV negativity. So those are the two actions we're choosing between. And as I said, there were lots of other actions we could put in here as well, but I just want to illustrate the maximizing expected utility story. So with action A1, the probabilities and uncertain outcomes and utilities are as follows. Here's a little chart. These are the 4 probabilities in the 2 times 2 equals 4 cells of that 2 by 2 table I showed you before. And in turn, they arise by cross-tabulating the dichotomy true HIV status plus or minus against the dichotomy ELISA status plus or minus. And let's think about what happens. If ELISA gets it right by being positive and the truth is positive, then we have only suffered a loss of $20, and I can make a loss into a utility by putting a minus sign in front of it. And so the utility associated with that particular situation is minus C1, which is minus $20. Similarly, in the last row of the table, if ELISA gets it right by being negative and the truth is negative, again, I have not made any mistakes, and so I again have a utility of minus C1. This work is sometimes expressed in terms of what are called loss functions rather than utility functions. But since loss is something what you want to avoid and utility is something you want to make big, you can go back and forth between them just by putting a minus sign on either one. C1 could be thought of as a loss, minus C1 is the utility. Now, what if ELISA says minus and the truth is plus? Then we lose something. And notice, this is the real rub about this way of behaving. You have to be able to think about what the real world consequences of that are, first of all. So this is the one where ELISA says minus and it's really plus. So that's the really bad one, right? And here's the trick. To actually do this, you have to be prepared to express the consequences of that happening in monetary terms, because C1 is already in dollars. So L sub Roman numeral 1 has to be in dollars. And similarly, in the third row down, if ELISA says plus and the true status is minus, you make a different kind of mistake. And so that suffers a loss of L sub Roman numeral 2, which would be a utility of minus L sub Roman numeral 2. So L1 is the false negative monetary loss suffered by this patient if he really is HIV positive, but ELISA says he's negative, and L2 is the false positive monetary loss that goes along with this. It may seem unpleasant and grim to be talking about the monetary consequences of being told you're HIV positive when you're not, and vice versa. But if you're going to try to use this theory to make choices in your life, you have to be prepared to get everything onto a common scale. That's what the theory says. And if part of your loss function or your utility function is in dollars, then all the rest of it has to come out in dollars also. Now, yes, please? Yes. In fact, in medicine, people often use something called quality-adjusted life years, QALYs, Q-A-L-Ys, which represents not only the number of expected years you expect to add to your life if you receive a certain treatment successfully, that's the life years part, but the quality-adjusted part, because the treatment might leave you in a state of diminished health in itself. So you try to take the expected increase in your survival time and adjust that for whether you are fully functioning or not. And so that's another metric. But the point of this theory is that all of the components of your loss function or your utility function have to come out on the same scale. And if it's easy to express one of them on the dollar scale, then the other one has to come onto the dollar scale too, or vice versa. So as a culture, how do we feel about this? Basically, I'm talking about putting monetary values on human life, monetary values on decreases in the quality of human life, for example. No one feels comfortable about doing this, and yet if you look at the logic here, if we were ever to try to create a rational healthcare system in which we were deciding whether or not to implement a particular treatment, we would have to face issues like what's the monetary value? You know, we know how much it costs to do this procedure. What's the monetary value in terms of equivalent human life, quality adjusted life years, for example, of doing this or not? The National Health Service in England does this all the time. They have a thing called the National Institute for Clinical Excellence, NICE, and they compile, they do meta-analyses of studies that are run in the medical literature to figure out things like what's the actual gain to the net health of the British population by spending £100 on tattoo removal versus spending £100 on giving extra food to a woman who doesn't have enough money to buy food during the period of her pregnancy, for example. Now that one's a no-brainer, right? You should give the £100 to the woman. But if I offered you two other things and it was much harder to compare them with each other, then it's going to have to come down to some way of comparing the cost of the treatment against the benefit of the treatment, and the benefit has to come out on the dollar scale or the British pound scale. Actually, we Americans have answers to these questions, even though they're not pleasant to talk about. We are a heavily litigious society, and every time an airplane crashes, all those ambulance-chasing lawyers rush in, and lawsuits are filed against the airplane company, you know, the airline, and also Boeing, and anybody they can sue, and the stuff all gets settled. And people get monetary rewards, monetary compensation based upon the loss of their family members. So the way they usually do it is it has two parts. One is they try to work out the amount of money that person would likely have earned approximately in the rest of their working life if they hadn't died in the plane crash. So think of someone who's 25 years old and relatively healthy and is making $75,000 a year right now, for example, and works from 25 to age 65. You can now do an actuarial calculation and work out how much money that is, approximately, how much it's likely to be. And then they also sometimes put in a component for pain and suffering. I'm not going to talk about that component, but just thinking about the other component, for example, and doing rough mental arithmetic, what, according to these lawsuits, is the value of that person's human life that was lost in the plane crash? I'll give you powers of 10, and you can tell me which one it's closest to. $10,000, $100,000, $1 million, $10 million, $100 million, $1 billion. Which one is the closest to? Or you could say between blah and blah in that scale. Between $1 million and $10 million. That's what a human life is worth. I don't like to say it that way, but that's what the law system says a human life is worth. And they compute it based upon things like that. So even though it's unpleasant to talk about, we are already in the realm of being able to think about the monetary consequences of either loss of life or partial loss of life. Do you remember those nasty old insurance policies? Maybe you even have one where you read in the fine print and it says, if you lose a leg, they're going to pay you $5,000. And if you go blind in one eye, they're going to pay you $14,000. They've already done this stuff, right? So these numbers are out there. And it's unpleasant to think about, but we have to think about this stuff if we're going to actually try to make rational progress in deciding how to spend our dollars on optimal health care for the country. The state of Oregon has begun to do this. The state of Maine has begun to do this. The same sort of thing the British are doing, they're now doing this. They have single-payer health care in the state of Oregon. They have single-payer health care in the state of Maine. And they're making difficult choices about whether to spend that $100 on the pregnant woman or whether to spend it on tattoo removal or whatever else the other thing was. I think that's right. I noticed this very same thing when I was about 8 years old. There was a very dangerous intersection near the house that I grew up in. And I kept asking my father, why don't they put a traffic light there? And he said, they have to wait until someone dies there to prove that it's dangerous enough to justify the expense of putting the light in. And sure enough, about a year and a half later, there was a fatal car accident there. And 2 months after that, they put a light there. And so you're right. That's another really bloodless, blood-curdling and bloodless at the same time sort of calculation that people make like this. That's exactly right. So it looks like it's lunchtime. We'll finish this calculation after lunch, or we could go another 5 minutes and finish it now and be wrapped up. Want to do that instead? Okay. So the point is, C1 is easy to quantify, but you have to be prepared to bring L1 and L2 to the table in this story. And even if you don't know what they are, you have to be able to prepare. You have to be prepared to talk about how much, in orders of magnitude, bigger one of them is than the other, for example. So now, to take the expectation, I just do the usual thing with random variables, right? I just go the probability times the value plus the probability times the value. I just make that calculation, and there's the expected utility under action 1. The corresponding table for action 2 is more complicated because we have to have a 2 by 2 by 2 table. The dichotomies are the truth plus minus versus what ELIZA says plus minus versus what Westernbot says plus minus. And the relevant 8 probabilities they arise from Westernbot's design. It turned out the goal was to have about the same false negative rate as ELIZA, but a much lower false positive rate. And the result was slightly worse sensitivity value, but much better specificity value. And so now, under the very top row, ELIZA says plus, and so we have to do Westernbot, and we get it right. And so we lose both C$1 for the cost of ELIZA and also C$2 for the cost of Westernbot, and that means a utility of minus C1 minus C2. The bottom 2 rows, by the way, ELIZA said negative, and so we just stop. It doesn't matter what Westernbot says. We declare, and ELIZA got it right, and so we declare negative, and it is negative, and so on. And so now we end up with a table that has those same L1s and L2s in it, and also every single row has a C1 in it, and some rows have a C2 in it for when you do Westernbot, and sometimes you don't. So in this action here, every row has a C1 in it, and in the previous action, every row had a C1 in it also. So C1 is going to cancel in comparing these two things. It just has to drop out, right? So now the expected utility comes out the same thing, probability times value dot 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 down, and you get this expression here. And by maximizing expected utility, you should prefer A2 to A1 if the second expected utility expression is bigger than the first one. And when you simplify, it comes out to that expression there. And if you look at it, the second action, the adaptive action, becomes more desirable as the loss suffered with a false positive increases. And it also becomes more desirable as the loss suffered with a false negative decreases. And it also becomes less desirable as the cost of Westernbot increases. And if you go and think about all 3 of those things, you'll see that they all make good sense. And now, to decide which action to do, you have to be prepared. We know what C2 is. It's the cost of Westernbot. You have to be prepared to do a sensitivity analysis. Put in some numbers for L1 and L2 and see whether the resulting expression comes out positive or not. That will tell you what to do. And it's interesting to note that with a modest value for L2, remember that's being told you're HIV positive when you're not, pick a value like $1,000 for that as a kind of not too bad penalty for you. The monetary advantage from taking action 2 is quite small, even with a realistically huge value for L1 like $100,000. Those 2 numbers together lead to an edge for A2 of only about $12, but then if we did this across thousands of people, that would really start adding up to something worth writing home about. And that's due to the extremely low false negative rate for both tests. With L1 equal to $1,000, L2 would have to be over $335,000 for A1 to dominate. And so the overall conclusion here is that for realistic values of L1 and L2, the adaptive strategy is better. And we'll see many more examples of maximizing expected utility as we go along in the course. And here's some references. And so let's go to lunch.